So we talked about reversibility and introduced the concept of ancilla to make irreversible functions reversible. So in this set of slides, we're going to talk about the mathematical reason why quantum operations are reversible. And it's because they're unitary. So we're going to look at unitary matrices in a little bit more depth. So quantum computation is reversible, as we've talked about, in the sense that we are able to recover output states. And one of the big takeaways of why quantum computation is reversible is because it conserves energy. So because energy cannot be created or destroyed, there must be 100% probability that the quantum state is either in ket 0 or ket 1 when we're talking about a single qubit. So because we have a 100% chance that we're in either one of these states, we have to make sure that our quantum operations respect that, and they do, and they are unitary. And because they're unitary, they are invertible. So what is a unitary operator? So an operator is unitary if it's a square matrix, and it follows this property where if you take the operation and multiply it by its inverse operation, you get the identity operation. Many operations act as their own inverse, and many of the gates that we've looked at so far in class and we'll be sticking with are ones that act as their own inverse. And there's a special term for that. It's called Hermitian or self-adjoint. We won't worry too much about the meaning of those words, but that's just a term that you'll often see in textbooks talking about gates that are their own inverse. So as a note, we kind of talked a little bit about this today. Whenever you have a quantum matrix that's transforming a state, it's going to be of size 2 to the n by 2 to the n, where n qubits is the number of qubits that are transformed by that operation. So we have our identity gate, which we've introduced today. The identity gate takes a qubit and outputs a qubit of the same value, so it does not do anything to change the state of that qubit. And then we can look at some of our matrices associated with the quantum operations we've learned in class. So we've learned about the identity operation, the NOT operation, our phase flip operation, and our Hadamard H operation. And let's take a little bit of a further look at, or let's look a little bit deeper into these operations. So if we look at all of the matrices associated with these operations, the elements in the matrix are mirrored across the diagonal. So this kind of is something that goes into, that plays into the fact that they are their own inverse. So if we look at the diagonal associated with all these operations, the elements are mirrored across the diagonal. So that's because one of the reasons that is because they are their own self-inverse. So let's look at what happens when we NOT twice. We've looked at this in class visually with what happens to the qubits when we send a qubit through a NOT operation, but we'll look at the mathematics to kind of confirm that you're able to get the output, or you're able to achieve an output that is equivalent to the input whenever you implement the NOT operation twice. So we have a qubit state that we're going to pass through the NOT operation twice. So in order to implement our state transformation with mathematics, we're going to write the matrices associated with X and our quantum state. So our vector associated with our quantum state here. We're going to keep it general. So we have a general quantum state we're transforming. So whenever we're implementing this matrix vector multiplication, we'll have to implement it step by step. So we're going to start here to evolve the state. So we'll do the multiplication of this NOT operation with alpha beta for our quantum state. That results in the flip of our state. So we have beta and alpha switched because we implement that NOT operation that causes those probability amplitudes to swap locations. And then if we implement the NOT operation one more time, we end up recovering our original input state. So let's try that again with a different gate. Let's see what happens when you implement the H gate simultaneously. So we're going to start the same steps. where we'll go ahead and write out our matrix for our H gate and our general quantum state, alpha and beta. We do our matrix multiplication. So we'll go ahead and take a step here. So when we do our first multiplication, we want to do rows times columns. So we have alpha plus beta in this top element, alpha minus beta in this bottom element. So this is our resulting quantum state. We're in a superimposed state. And now we'll go ahead and look at the second evolution of the state through the second Hadamard operation. So we have alpha plus beta, and that's going to be, so we're going to do our rows, columns, multiplication again. So we have alpha plus beta plus alpha minus beta in this top element, alpha plus beta minus alpha minus beta. And if we cancel out some terms, we can see that we have alpha plus alpha, beta minus beta. So we're going to have 2 alpha on top, alpha minus alpha, beta plus beta, 2 beta on bottom. And then, of course, when we take these coefficient terms, multiply them together, we get a 1/2. So our resulting state is 1/2 2 alpha over 2 beta. If we go ahead and simplify, we see that our resulting quantum state is alpha beta, so our original quantum state. So by passing through that state through the H gate twice, we're able to recover it. So that kind of goes to show that the H gate is reversible, and it's its own inverse, because if you pass through the gate twice, you end up recovering your original input. So let's look at matrix multiplication. So whenever we are computing an operation represented as a matrix times its inverse, we want to make sure that we get the identity operation. So typically matrix multiplication is not cumulative or commutative. So matrix multiplication is not commutative. But here in this case, for our definition of unitary, it is. So we can take a matrix times its inverse or an inverse times the matrix and get the identity. So we'll see this in action. So we're taking 2 matrix, 2 by 2 matrices, and we're going to multiply them out. And we can see that we follow the same procedure of row times column. So we have matrix, resulting matrix. We're going to implement alpha, or A times E plus B times G to get this first element. A times F, B times H to get this second element. C times E plus D times G to get this third element. C times F plus D times H to get that last element. So that's how you implement your matrix multiplication. It's just a slightly more complex operation than matrix vector multiplication, which we've done many times. So bonus example 3, we're going to test that unitary definition. So we have our Hadamard operation, and we're going to confirm that that H gate is indeed unitary because it follows the rule that we define for unitary operations. So let's take H times H. So as a note, this is a matrix multiplication operation, not a tensor product. We're not having that circle around our multiplication operation. So this is just a multiplication. So we're going to multiply these 2 matrices. So we can see what happens here when we multiply it out. So to get our first element, we do row times column to get this first set of elements here. So we have 1 times 1 plus 1 times 1. 1 times 1 plus 1 minus 1, 1 times 1 plus negative 1 times 1, and then 1 times 1 plus negative 1 times negative 1. So of course this is going to result in a positive 1. And then we have our coefficients that we pull to the front, multiply those to get a half. So we're left with 1/2 multiplied by 2. We simplify that and we get the identity operation. So therefore you can end up with your starting state if you pass through H twice.